A type 1 error is rejecting the null hypothesis when it is actually true. So when we state our hypothesis, both of them, our null and our alternative, this was their innocence, we were thinking, and this is their guilt. Rejecting the null hypothesis when it's actually true would be like saying someone is guilty when they actually were innocent. So think about it. If you were charged with a crime and you were charged guilty, but you were really innocent, being innocent was really true. So that's a big error. And the numerical value of that type of error is exactly what you were testing. So if you were testing at a significance level, you were trying to see at 0.05, if that was your alpha, your significance level, then your type 1 error would be about 5%. So one way to lower your type 1 error is to be more picky and say, well, I'm not going to compare against 0.05, I'm going to compare against 0.01. And then if it's lower than that, I'm going to reject it. And that's great because it will actually bring your error down then to 0.01, whatever that number is there. Now the thing is there's a balance because a type 2 error is failing to reject the null hypothesis when it's actually false. That means you have your innocence and you have guilty. And it's failing to reject the null hypothesis, so you feel someone is innocent when they've actually committed the crime and they're actually guilty. And that's a pretty big problem too. You figure you wouldn't want to declare someone innocent and let them out on the street if they were actually guilty of the crime. Your type 2 error is not something you'd have to calculate, but because it requires you to have a power. And if we wanted you to calculate it, we would give you what that power value was. And the type 2 error, how you calculate it is you do 1 minus the power. Now the thing is that if you wanted to try to minimize your errors, the top one, we could be really, really picky, right? And we could go to 1%. And if someone is getting lower than 1%, we're going to reject the null hypothesis and basically state they're guilty, something like that. When you lower your type 1 error, you actually lower the power as well. Well, what happens when you lower the power is you would actually increase your type 2 error. So you have to have a healthy balance. You don't want to make it super, super strict because then you're going to end up lowering your power, which then raises your type 2 error level. One thing that everyone can kind of agree on is a large enough sample size helps everything. Now, we've talked about it before, not too large, but as big as you can would be something that would keep everything in balance. Let's try doing a significance test again and seeing if we can set them up and how we do. So we're going to compare to alpha is 0.05. And what we're getting is our end value is called a p-value, and that's what we're going to compare against it. If our p-value is lower than that, then we're going to reject. And if our p-value is higher than that, then we are going to fail to reject. Those are the words that we use to do it. So setting up our null hypothesis and our alternative hypothesis, this is where our equals is. And the other one is our less than, greater than, not equal, something like that. So this is kind of what we're expecting to happen, our baseline. And we expect for everybody to have a 1/12 shot. And that also works out to like 0.083. Our alternative hypothesis is that preferring the last contestant viewed. So saying that the person has an advantage to going last. It seems like if you were out of 12 people, you'd have about an 8.3% chance of people liking you. If you've got an advantage and people are liking you more than everybody else, to me, I would think that your probability would be greater than 0.083. Maybe people like you 10% of the time, or 15% of the time, and everybody else that much less. The next start is trying to set up our z-score, and that's basically what it is. Our standardized test statistic, and this is right from your packet, equals the statistic minus the parameter over the standard deviation of the statistic. And how we've been doing this is we've been doing a z for proportion. What did we get? We got 59 out of 600. That's our statistic. 59 out of 600 is about 0.098. So that's what we got from our sample. Perimeter is what we expect our population to be. We expect everyone to get about an 8.3% chance. And when we do the standard deviation of the statistic, that's this one where we were figuring out the standard, and it says it right on your sheet as well, standard deviation of the statistic. With proportions, you would do your original p-value, not your sample p-value, times the q, which is like 917, divided by n, which is 600, 0.011, something around there. For my final result, yeah, like around 1.36, maybe something like that. And then we've got to actually look in the chart and see z-score of 1.36, 9131. Probability 1.36 is 9131.9131. But our alternative hypothesis is saying greater than. So we're trying to see the greater than version. Remember, this is a z-score. This is giving me here and all of it below. I want to know what's greater than this tiny little section over here. 1 minus 0.9131. So like 0.00869. This is our p-value. This is what we're comparing to 0.05. If it's lower than it, then we say there's no way that this could possibly occur by chance. There's something rigged. Something's wrong with this. Since it's higher than, we're going to fail to reject the null hypothesis. So let's turn the page and write exactly the wording that we like to have on something like since the p-value. You could state what the p-value is. Since the p-value is greater than alpha, and you could state that value as well, we fail to reject the null hypothesis. Think about what the hypothesis was measuring. Greater than having an advantage by going last. So maybe something like we cannot conclude that there is an advantage to performing last. something like that. One thing before we finish, let's go back to the front for a minute, the front page. And you always want to check your condition. Were the people selected at random? And it says it. Did we take 10% or less from the people we have to pick from? In the sample, you're taking 600 Americans. I think there's like millions of Americans that are American Idol fans. So I think you can say check to that one. And this is the NP is greater than or equal to 10 and NQ is greater than or equal to 10. That is a really small percentage, 0.098. So when you're multiplying by 600.098, this would be the one. If there was going to give you any problems, I would think this would be the one. And when I multiply it, yeah, this gives me 58.8. So this one checks. I'm sure then if I were to multiply it by the opposite, the bigger number, it would work too.